Okay, so good morning, everyone. Thank you for logging in today. I'm excited to be at home talking about rock. So I'm going to talk today about work that my group has been doing for a while on looking at strain localization at oceanic transform faults and the way in which our view of these rocks has changed over the years, and in particular, the emphasis that we now place in hydration in the fault for not just the upper level of the fault, which you would expect, but getting in really deep into these fault systems, into the rocks, such as the one that I'm showing on this first slide here. I'm going to walk through the evidence that we have today that hydration seems to be really central to the shear localization on these faults. And this is work actually that I started doing with Greg Hirth a long time ago, and has more recently been picked up by my postdoc, Cecile Prigent, who actually will be starting at IPGP as a professor in a month or so. And then also Arjun Kohli, who's a research scientist at Stanford. Monica Wilson-Schwer, who has done a lot of the numerical modeling for this, and who's currently based at MBARI. And then work that my student Mindy Baruth is beginning to do as part of her PhD work. And finally, a collaboration that we started with Christian Tessier, partly from talking about similarities and differences between looking at oceanic rocks and continental rocks. So what I want to get you to in the talk today is our new view on these transform fault systems. This is a figure that Cecile put together in her 2020 EPSL paper, showing that seawater flow in these fault systems is getting in really deep. Our estimates now, because of the formation of very high temperature hydrous minerals, is that the temperatures that these are forming at are up to 900 C. And depending on the thermal structure of the fault, that can be fairly deep somewhere, at least in the transform fault system, it's deep somewhere up to 20, even 30 kilometers we've estimated for these systems. And that the role of seawater in getting to these systems, we're beginning to think is really driving the mylonitization and the grain size reduction process. And that we're also seeing, as we go deep in these systems, a transition, or not a transition, but that we have both brittle and ductile processes operating at the same time. Okay, so that's what we're going to end up with today, but I thought I would give the preview on that. Transform faults, the oceanic view of the world is that the map looks like this. And the transform fault view is that all of these black lines are oceanic transform faults. Their combined length is around 16,000 kilometers. This is a figure from a really nice paper by Margaret Betcher and Tom Jordan that looks at the seismicity on these faults. And one of the things about working on these transform faults is that we do have a lot of constraints on the active tectonics and knowledge of things like the slip rate, the age of the fault, those types of constraints when we work on these rocks. We also have the advantage that we are in a fairly simple lithological system. Yesterday, there was discussion about the role that the pre-existing heterogeneities might play in a system, or localization against different lithologies or weaker lithology. In the case of transform faults, we're in this fairly simple system. We have pillar basalts underlain by the sheeted dites, underlain by gabbro, and then the transition through the moho into the lithospheric peridotite. The brittle to ductile transition in most of these faults is either at the moho or well within the mantle. And most of the rocks that we have, most of the deformed rocks that we have from these systems are deformed ultramafic rocks. And so a lot of the work that we've done on them is focusing on the ultramafic part of the system. And in fact, we're only recently beginning to get into the mafic part of the system with new samples that have been collected. But this is to say at the moment that these are relatively well-constrained systems. You know, we're not trying to guess about different types of continental crust that could be down there. This is oceanic lithosphere with a reasonably simple structure. And so we expect, you know, the shallow part of the fault to be dominated by brittle processes. There's a photo on the right here of breccia that we just collected last November on a cruise where we were sampling the upper part of the fault. But what we've historically looked at are these mylonites that have been sampled by dredging. And this is this upper sample is actually a basalt breccia. This lower sample here, the mylonite, is a peridotite mylonite that comes from the brittle ductile transition on a transform fault. And so we expect a relatively simple strength depth profile. There should be some change in slope as we move between these lithologies. But the game in terms of thinking about ductile shear localization is really down at these higher temperatures in the ultramafic system. 600 degrees C has traditionally been taken as the brittle to ductile transition. But as you'll see with the data in this talk and other work that's come online in recent years, that's not a hard and fixed transition. And we can have ductile processes at lower temperatures, and we can also have brittle processes at higher temperatures. And I'll show you that evidence for that. So what do the rocks tell us about these faults? What can we do with them to understand plate boundary formation? Again, we have now more and more of these brittle samples. This is a photomicrograph on the left of a mafic breccia that we collected last November from Gofar Transform Fault. This is about as far as we've been able to get with it analytically, but we're hopeful that we'll be able to get it in the lab soon to do something more quantitative with it. What we have been looking at for a while now are what we would classify as these semi-brittle mylonites. This is now a peridotte mylonite. We call it semi-brittle because there are these crust-cutting fractures in these samples. Some of them fully crust-cut. Some of them have clearly undergone shear offsets. And so you had a brittle event and a later ductile event that happened in these samples. And then these samples over here on the right that we would call the fully ductile samples. All of these are evidence for strain localization in the transform fault system. And we now have samples of the mylonites, at least, that come from about 11 transform faults globally. This is a figure from a paper that Arjun Kohli has submitted that includes a compilation of everywhere that we've been able to track down records of mylonites being recovered. So all the circles indicate places where mylonites have been sampled predominantly by dredging. There's a little bit of dive work that has been done. And so the limiting factor in terms of thinking about this is that there is a sampling bias because in almost all cases, the dredging that's been done is not dredging with a focus on sampling the transform fault zone and getting at the deformation. It's dredging that was done to look at often just the deeper lithospheric portion that's exposed in the transform fault wall. And so the dredging hasn't been focused on deformation, it's been focused on getting deeper lithologies. So we don't have sampling that really reflects what is probably down there in terms of the fault exposures. We just happen to have kind of lucky finds when the dredge hit the fault zone. Again, the transform valleys are often 10, 50 kilometers wide, but we think that that zone where the fault is exposed is probably something more like 100 meters to half a kilometer wide. So you have to, with dredging, get fairly lucky. We did last November go to Gofar Transform Fault, which is over here on the left, and actually systematically sample it. And that is how we have a much more comprehensive set of fault rocks from there. In this case, what we have are breccias. The other faults that I'm going to talk about today predominantly are the Shaka Transform Fault and the Prince Edward Transform Fault. And those are the case of dredges done in the late 70s and early 80s that happened to collect a large volume of mylonite. And they really give us a lot of material to work with in terms of understanding what's going on in the fault. And of course, this is a limitation, right? The field area is the ocean, and we don't have the types of observations that we would have if we were looking at a shear zone on land. So we can't really tell you the width of the shear zone. The samples that we have are not oriented samples, but they still, we can still do a lot with those samples. We have started to try to create profiles of what the fault system must look like. Again, when you only have dredging results, it's very difficult to do. And so this is an example of what we know and also of what the limitations are. So Shaka Transform Fault on the Southwest Indian Ridge is where we have some of the best dredges of mylonites. In this case, a whole bunch of dredges were collected. All of the stars, this is a little map. This is the fault itself. This is the dredges that were collected. There were 7 dredges that were done here. It's really dredges 60 and 61 that collected a lot of mylonite. And this is, we have a single pass of shipboard bathymetric data. And from that, we can take a profile of what the slope looks like. There's a little step here, which we guess is the fault exposure itself. And this is approximately where dredge 60 and then dredge 61 did sampling. And the main stuff that they recovered were mylonitic samples. For comparison, some of the best constrained observations that we have for transform fault are from Vima Transform Fault on the Mid-Atlantic Ridge. This is work done by Enrico Bernardi and many of the people that he has worked with over the years. There's a very long ridge here on the south side of the fault. The stars indicate all of the sampling that's been done by dredging. The red stars, again, are where the mylonites were collected. And then in addition, there was some in situ dive sampling that was done as well. And taking all of that combined, there's a profile that was put together that estimates that there's multiple slivers or strands of this fault exposed at the seafloor. In some cases, it's inferred to be in some of the mafic units, but the mylonitic peridotites are coming, thought to come from the lower part of this zone, and that there's possibly multiple strands to the fault. So that is what we kind of have in terms of field constraints. In future years, we are hoping even in the next year or so to get some Sentry, some autonomous underwater vehicle-based observations. But the exposure on the seafloor is still, you know, often difficult to discern the structures. So it's a challenging setup in that sense. But the other things that we do know really well in these systems, and so one of them is that in the last decade or so, we've gotten really good constraints on the thermal structure from improvements that have been made to how these are modeled. So this is work that Mark Bain started it back in 2007. And we've been working more recently with Monica Wolfson-Schwer, who's been doing modeling of segmented transform fault systems. And in this figure from Mark Bain's paper, one of the key things is that they've moved beyond just taking a simple half space cooling model, which is what the black line shows here, where you would essentially taking the half space cooling for either parts of the oceanic crust coming off the ridge and juxtaposing those. In this case, they are running a full geodynamic model that incorporates both the brittle rheology and the temperature sensitive viscosity for the ductile part. And what they find is actually that the thermal structure is somewhat warmer than previous estimates from half space cooling would imply. And this actually meshes much better with the ocean bottom seismometer data and earthquake locations that have come online in the last decade, and that you can really understand the seismicity better in using these newer models. For the Shaka transform fault that we're going to look at some samples from, this is what the model looks like for that system. So this is a model that Monica Wolfson-Schwer ran as part of the work with Arjun Kohli. Again, this is the ridge axis here is shown by this bit and then by the bit over on the right. And then the main bit in the middle is what the transform fault itself looks like. The MOHO, we don't have any constraints on the actual MOHO depth here. I've just put it at a nominal 6 kilometer depth. It's likely a lot shallower in this system because we know from dredging in the fault and also in the adjacent ridge that there's very little crust around. But to some extent, we're not too worried about that because in this system, the brittle-ductile transition, if we assume that's represented approximately by the 600 degrees C isotherm, is fairly deep. It's somewhere around about 14 kilometers depth. You can play around with aspects of the model to try to get that a little shallower, but we're still finding that the mylonites, and we see this with all the places where we've looked at what the temperatures are on the mylonites and therefore what their corresponding depth is based on these types of models, that the mylonites exposed at the seafloor seem to be coming out from quite a depth by the time we're getting them. We, again, because we don't have a lot of field constraints on what the fault exposure is like and can't really trace that, we don't have good constraints on what that emplacement mechanism is, but we know that we need to be getting those rocks out from very deep based on everything that we see about the pressure and temperature conditions for their formation. So the protoliths, again, in the case of looking at ultramafic rocks, we have a good constraint on what the protolith is. We've looked at a lot of, prototypes globally that are not deformed, and they generally look like this sample on the left here. This is a really pristine sample, actually, that came from the Tonga Trench. It's predominantly composed of olivine or the rainbow colored stuff in this cross-polarized photomicrograph. The orthopyroxene here are also fairly large grains in the kind of gray and white colored grains here. There's some amount of spinel in this sample, and there may or may not be clinopyroxene present in these samples. And then we know from having looked at these for a while that as you have deformation and go to a very fine grain size, you produce these prototype mylonites that have a grain size orders of magnitude smaller than what the protolith started out with. Way back a while ago now, Greg Huth and I looked at one of these samples to look at what was driving the accommodation of deformation in the ductile regime. We focus on areas such as this, which is fairly fine-grained, and we're able to collect EBSD data on those samples. showing that there seems to be some mixture of what we mapped as orthopyroxene at the time mixed in with olivine, and that the olivine had no lattice per photo orientation. And this is an observation that other groups have made as well in looking at Peridotte Mylonites, that when you go to very fine grained material, that the olivine has no LPO, and that implies it's in a grain size sensitive or diffusion creep deformation regime. You can see in our map back from a while ago that we did not have very good resolution in looking at this sample. We aren't really able to resolve the individual grains when the grain size is around 1 to 10 microns. Things have improved considerably since then, and hence our knowledge of these samples has really changed. So this is an EBSD map that Cécile Prigent collected a year or two ago. In this case, looking at a sample that's shown down here, the photomicrograph, it's actually fairly coarse grained, except for this very fine grained shear zone that cuts through it. And her map nicely shows that in the coarse grained region, we have fairly monomineralic olivine, but in this fine grained region, we have a lot of other phases that are present. But the phase that really dominates in this region is the one in turquoise amphibole. And so this has been one of the really big changes for us in how we look at these samples, in that there is a large amount of amphibole present in these fine grained zones. It's not just pyroxene that is present. And in fact, the amount of pyroxene that's present is often fairly low, which is an indication already that the amphibole is forming at the expense of the pyroxene. In the case of this sample that I'm showing as an example, there's also plagioclase present, which suggests that there had been some amount of melt that happened as well. But the large amount of amphibole and some of the other observations I'm about to show you has led us to this conclusion that hydrothermal fluids got into these rocks and actually assisted the high temperature deformation and associated with metamorphic reactions where the pyroxenes are reacting with the water to form amphibole in these samples. So what are the other observations for fluid flow in these rocks? One of the things that Arjun Kohli started looking at a while ago was the fluid inclusion planes that are present in these samples. So in these mylonites, there are these relict porphyroclasts and partially recrystallized areas. And when you zoom in on them, you can find these fluid inclusion planes that are present in them. They do not continue out into the ductile matrix. And it's hard often to find those inclusions in the ductile matrix, which is an indication that the fluid inclusion planes have to have predated the ductile deformation. So that's one line of evidence that there was hydration in these rocks, even up at relatively high temperature, high pressure conditions. Another thing that we started looking at was stepping back from our favorite samples in some of these dredges, which are really beautiful mylonites, and looking at the wide range of material that was recovered in some of these dredges. So I said before that the Shaka and the Prince Edward transform faults recovered these really nice dredges of Peridotte, and it's not of mylonite. It's not that they just recovered one mylonite, but it's that they actually recovered entire suites of rocks that are all deformed to some extent. And for years, we really didn't pay attention to these other types of samples. And I was really fortunate that when Cécile Prigent joined my group as a postdoc, and I handed her these box of samples, she not only was excited to pull them apart, but really figured out systematics and really taught us something new about these rocks. So in this summary slide, she's put together examples of different types of alteration mineralogy and evidence for fluid flow in the rocks. So we have cataclasites and also the more recent mafic breccias that we've been looking at. In the cataclasite, we know that we have serpentinite that's cutting through. We have these talc serpentine schists that are clearly ductily deformed. But as we go to things that we would treat as kind of high temperature mylonites, it turns out that they also have hydrous phases. And in the case of these examples, these are also chlorite bearing samples. Cécile took this a step further and really figured out some nice systematics on this. She recognized that there is the low temperature mylonites that are serpentine bearing. Because they're serpentine bearing, we know that they formed at somewhere less than 500 degrees C for serpentine to have been stable. She also recognized that there's a class of middle temperature mylonites, which are defined by the composition of the amphibole and also the presence of chlorite. And then these high temperature mylonites that also contain amphibole, but it's a high temperature amphibole that's present. And so looking at the photomicrographs of these types of samples, the low temperature deformation is defined by containing an assemblage that's serpentine, chlorite, and low temperature amphibole might also be present. Medium temperature deformation has chlorite and low temperature amphibole. And then the high temperature amphibole, high temperature deformation is characterized by containing what is a high temperature amphibole. In these photos, she's also highlighting that there are both ductile fabrics in these rocks, right? So the white line is showing you the foliation in the rocks, but also that these have cross-cutting fractures. And at all temperatures that we're seeing both ductile processes and also brittle processes occurring in these samples. I said that we have these high temperature amphiboles in the samples. So how do we know that? And that's some really nice thermometry work that Cecile did by electron microprobe, looking at the amphibole compositions. And the data that she got back was pretty surprising, because until she did the quantitative analysis, I was pretty sure that we were just going to find that these cross-cutting fractures were late stage and had a low temperature amphibole in them. But what Cecile's results showed is that actually in the high temperature mylonites, all the amphibole, whether it's in a fracture or in one of the shear bands, is effectively the same composition. So this is a plot of the amphibole composition in silicon atoms per formula unit. And it's actually plotted against the chlorine content. And that's because the chlorine content was surprisingly high in these samples. But you could also say it's not surprisingly high if the origin of the water in these rocks is seawater, right? So the chlorine content, depleted mantle has a chlorine content that's less than 10 to the minus 4 weight percent, but seawater sits up here around 1 weight percent chlorine content. And so the amphiboles that formed have very high chlorine contents, which is indicating that it must be seawater, apart from the high abundance of the amphibole as well. And that we can also use the composition of the amphiboles to estimate the temperature. So the amphiboles range from being tremolite when they're lower temperature through magnesio hornblende up to pagosite, right? So the high temperature mylonites tend to contain the high temperature pagosite amphibole and some magnesio hornblende. And then the medium temperature mylonites have these lower temperature magnesio hornblende into tremolite. And then the lower temperature mylonites that we've actually not looked at in as much detail tend to contain more tremolitic amphibole. So we know from looking at these mineral compositions that we have seen fluid flow at temperatures at least greater than 700 degrees C to be forming amphibole of this composition. We have in these high temperature mylonites, these beautiful ductile fabrics that have formed, very intense ductile deformation. But this is where this assumption that the fractures cross-cutting them were late stage we learned was incorrect. So the photomicrograph here of one of these high temperature mylonites shows these nice shear bands that we assume accommodated the deformation parallel to the foliation, and then these cross-cutting fractures. And when Cecile mapped this with EDS, what we found and confirmed with more quantitative microprobe data is that the yellow fractures are filled with amphibole, but it's the same amphibole in the fine-grained shear zones that are present here. Again, you have this much more multi-phase layers that are the finer grain layers, and then the coarser grain layers, coarser olivine grain layers in between those. But that amphibole was also a high temperature event in these rocks. In addition, Cecile identified these really beautiful shear offsets of those high temperature fractures. So in this high temperature mylonite here, you have these very fine grained shear zones, these brown layers, coarser grain material, and then these cross-cutting fractures that are filled with high temperature amphibole, and then they've been subsequently undergone shear offset. So we now have a much more complex set of processes where fluids are getting in very deep into these systems with brittle fracturing processes. And it's, we're beginning to look at the fact that the brittle fracturing and is leading to some of the grain size reduction, and then the nucleation of new phases of the amphibole and other hydrous phases in these very fine-grained shear zones, so that you end up with very fine-grained olivine that can then take over for ductile deformation. So the combined evidence for deep circulation of seawater, one is that we have a lot of hydrous minerals in these rocks, which requires addition of seawater, particularly with the chlorine contents that they contain. We have cracks that indicate semi-brittle behavior at very high temperature, above 600 degrees C. We would estimate up to 900 degrees C. And that those fractures also had shear offsets that indicate alternating brittle and ductile behavior. And if I have 2 more minutes, I'll just stick this on a rheological profile. So what does this tell us about the rheology of the fault? So this is now a strength depth profile constructed for the Shaka transform fault. So the thermal structure we know from the thermal modeling that Monica Wolfson-Schwer did. And then we've estimated what the, both what the ductile strength of the rock is, and then also what the frictional strength of the rock is, both if we had initially just peridotite, and then if we have serpentine forming, we would have a weaker rock. And then when we go from the protolith shown in gray here, which is the coarse grain peridotite forming by dislocation creep or grain boundary sliding, as you move into the high temperature mylonites, we estimate with that grain size reduction that we're moving into a weaker, we're moving into diffusion creep, and that can accommodate ductile flow at a shallower depth than the coarse grained rock, and that we have increasing shallowing on the fault with these changes in the rheology of the system due to the grain size reduction of the olivine. But that grain size reduction really seems to be linked to the formation of the hydrous phases and the metamorphic reactions going on in the rock. And so this is my last slide now. So this is our conclusion, which is that hydration is controlling the fault rheology, is leading to nucleation of new phases, but it also seems to be driving the grain size reduction process in these rocks. And that we have this interplay between brittle and ductile processes, that there's not a hard boundary on that brittle ductile transition, but that is moving around as fluids get into the system and change the strength of the rocks through the changes that they induce. So thank you everyone for listening, and I'm happy to take questions now.
Thanks a lot, Jessica. So really nice talk. So I'm sure there are lots of questions. So for questions, it's nearly easiest probably to type them in. Raising your hand is also possible, but let's start with some questions. Okay, first question from Drew Levy. Great talk. Perhaps a simple question, but how is the moho shallower than the brittle-ductile transition zone, as you showed in the thermal models? So if you go... Yep.
Yeah, I can go back. Let me just see, because I might still have a slide comparing the two. Or I might have taken it out. Okay, let me go back to the Shaka example. Right, so with the Shaka transform fault, this is the thermal model that Monica Wolfson-Schwer ran for us. And the moho, I just put on at a 6 kilometer depth. Oceanic crust has an average thickness of 6 kilometers. Though actually in this system, because this is a really, really low spreading rate, the moho should actually be shallower than 6 kilometers. The brittle ductile transition for mafic rocks, really for olivine, is expected to be somewhere around 600 degrees C, which is based on both lab observations actually by Margaret Betcher for where the transition from brittle failure to ductile flow occurs in olivine, which is around 600 degrees C, and also constraints from seismicity, which shows that in general, the large earthquakes at least don't occur at deeper than 600 degrees C. So the brittle ductile transition is defined from the rheology, both from the rock deformation constraints and also the seismology, whereas the moho is just defined based on kind of classic oceanic lithosphere structure.
Thanks. Maybe, so there are lots of questions. We can't take all of them, but the nice thing is we can keep the chat. So maybe also Jessica can take up some later. But one of the things that I saw here more on the metamorphic side, why do the high temperature amphiboles have a stronger seawater signature, so that's your chlorine signature, than the medium temperature one? So how does that work?
Yeah, that's a good question. That is simply with the changing composition, the ability of the amphibole structure to incorporate chlorine changes. So it's It is confusing because that negative relationship would imply somehow that there's more seawater in the high temperature amphiboles, but it's simply the ability of amphibole to accommodate chlorine in its structure that is changing.
Yeah, thank you. So maybe another one more on the fluid rock interaction. I just pick up some questions. So for the fluid rock interaction, do you have some direct evidence? Do you see any dissolution features, for instance, or is it mostly just the reactions you see?
So we do also, we've also looked at, so I don't have the figure, I don't have the images in this presentation, but Cécile Prigent has done some imaging with SEM to look at essentially the 3D structure on the surface of the grains, and has imaged porosity and also some dissolution pits as well. And actually, we've taken as a guide a lot of the work that's been done on continental mylonites, looking at the porosity in those. And we're seeing very similar features in these prototype mylonites in terms of those kind of etches and things on the grains that have been observed in continental mylonites that have seen fluid flow.
Okay, thank you. I think, thanks Jessica again. There are lots of questions, lots of interest, which is great. But we have to move on, and I'm sure some of them will come up in the discussions, but hopefully there can be some interaction on the side with the chats as well. So Susanne, do you want to take over?
Thank you,
Thanks
everyone.
again, Jessica.